sodium, NCM, mid-nickel, or LFP. Battery industry news has been largely focused on cathode materials. But a battery has two sides. What about the anode? When the first lithium-ion battery was introduced in 1991, the anode material was graphite. Even today, in most EVs, the anode is still graphite. While cathode materials have continued to advance, the anode has remained nearly the same for more than 30 years. An anode is just as important as a cathode in determining how much energy a battery can store. Most lithium ions are stored on the anode side when a battery is charged. Graphite can store about 372 mAh per gram. It cannot hold more because of its layered structure. Only one lithium atom can be stored for every 6 carbon atoms, known as lithium carbon-6, which limits the energy density. To overcome this limit, researchers have been searching for new anode materials that can store much more. Among the many candidates, the most notable one is silicon. Silicon, widely known as a key semiconductor material, is drawing attention again. The reason is simple. It can store much more energy. Graphite can store 372 mAh per gram, while silicon can theoretically store about 4,200 mAh per gram in the form of lithium 4.4 silicon, which is more than 10 times higher. The reason is its atomic structure. Graphite stores 1 lithium atom per 6 carbon atoms. Silicon stores up to 4.4 lithium atoms per silicon atom, enabling far greater energy storage at the same weight. Its operating voltage is about 0.4 volts versus lithium metal. Compared with graphite at around 0.1 volts, the voltage is less favorable, but stable enough for operation, meaning it still works with lithium ion. Silicon also offers strong resource advantages. It is the second most abundant element on Earth, even more abundant than sodium, which we covered in a previous video. It can be extracted easily from sand, and refinement and processing technologies are already well established through the semiconductor industry. With all these strengths, you might be wondering why silicon has not been widely adopted yet. Despite more than 30 years of research, silicon batteries still face a critical challenge. The biggest issue is volume expansion. When lithium inserts into silicon during charging, silicon can expand to nearly 3 times its original volume. It shrinks during discharge and expands again during the next charge. Repeating this cycle hundreds or thousands of times causes major problems. The first issue is particle fracture. The repeated expansion and contraction create strong mechanical stress, similar to stretching and releasing a rubber band, until it eventually snaps. When silicon particles crack or break apart, the electrode structure collapses and battery performance drops sharply. The second issue is loss of electrical contact. Silicon particles must stay in contact with the copper or aluminum current collector for current to flow. If the particles detach due to expansion, the electrical connection is lost and the stored energy can no longer be used. The third issue is instability of the SEI layer. The SEI is a protective layer formed from electrolyte decomposition. It prevents direct reactions between the electrolyte and the anode. When silicon expands, the SEI layer cracks and new surfaces are exposed. A new SEI forms repeatedly, consuming lithium and electrolyte until capacity and cycle life decrease significantly. In experiments, silicon anodes often show rapid capacity loss after repeated cycling, while graphite can retain more than 80% of its capacity even after 1,000 cycles. This is why silicon has not yet replaced graphite. Think of a soda bottle that is repeatedly heated in a hot car and then frozen in a refrigerator. It swells and shrinks until the bottle bends, cracks, and leaks, and the soda no longer tastes the same. Silicon expansion behaves in much the same way. To address these issues, researchers are exploring 3 main approaches. First, redesigning the structure of silicon to reduce expansion. Second, designing binders and electrodes that prevent silicon from breaking apart. Third, improving the electrolyte and the SEI so they are not consumed repeatedly. Let's look at how these approaches work. Before we dive in, don't forget to subscribe to the channel. The most important question is how we can redesign the structure of silicon to suppress its expansion. The first strategy is nanosilicon. By reducing silicon particles to the nanometer scale, roughly 100,000th the thickness of a human hair, the mechanical stress from expansion can be dispersed more effectively. It works on the same principle that large rocks crack easily, while grains of sand don't break even under pressure. A research team at the University of California demonstrated stable cycling for more than 1,000 cycles using nanosilicon smaller than 10 nanometers. The second approach is porous silicon. Tiny internal pores give the material extra room to expand. A sponge does not swell when absorbing water because the water fills its internal space. Similarly, engineered pores in silicon help relieve mechanical stress during expansion, and multiple studies have confirmed the benefits. The third approach is to combine silicon with other materials. Silicon carbon composites mix silicon with graphite or carbon nanotubes to leverage the strengths of both materials. Carbon provides strong mechanical stability and high electrical conductivity. Coating silicon with carbon or dispersing it within a carbon matrix cushions expansion while maintaining electrical contact. This allows higher silicon content while improving cycle life to a practical level. In one experiment, a composite with about 48% silicon delivered around 1,500 mAh per gram in reversible capacity, meaning about 91.9% stayed usable after repeated cycling, roughly 4 times higher than graphite. And using silicon oxide, which bonds with oxygen, can also help mitigate volume expansion because its particle size is more than 10 times smaller than that of silicon-carbon composites, making it more effective at suppressing silicon's volume changes. During cycling, the oxides formed within the material act as a buffer that absorbs volume fluctuations. Binders that can withstand expansion are also being actively researched. A binder holds silicon particles and the current collector together. Since silicon can expand up to 300%, conventional binders cannot tolerate repeated expansion and contraction, causing electrode damage. Researchers are developing more flexible and ion-conductive polymer binders. For example, Argonne National Laboratory combined PAA with a cross-linking agent called TEGDA to create a new branched polymer binder. This structure reduced electrode expansion from about 110% to around 10% even after 150 cycles. Another key solution is preventing electrolyte loss and stabilizing the interface. One of the most widely used and proven additives is FEC. FEC forms a stronger and more stable SEI layer on silicon, helping it withstand severe expansion and contraction. High-concentration electrolytes using lithium FSI salts are also becoming more common. They form a denser SEI that breaks less easily and reduces electrolyte consumption. By combining redesigned silicon structures, high-performance binders, and more stable electrolytes, researchers aim to improve both cycle life and safety. The technical breakthroughs are clearly taking shape. So how close is commercialization? A pure silicon anode is still in development because volume expansion remains a significant issue. While many papers report silicon content above 30%, most cells fail within 20 to 50 cycles. There are also challenges beyond performance. Cost. Even though silicon is abundant, preparing it as an anode material requires complex processing and expensive equipment. Graphite, in contrast, uses well-established, mass-production-ready processes like coating and heat treatment, which make it far more cost-efficient. This is why the industry is commercializing silicon composites instead. The first real-world mass production use was 5% silicon back in 2019 by LG Energy Solution. Reports indicate Panasonic and Tesla are using composites with about 10% silicon for some cases. Silicon composites are more expensive, but anode materials account for less than 10% of total cell cost. Considering the gain in driving range, adopting silicon composites is seen as highly practical. Do you think silicon batteries will become widely commercialized? What do you think about pure silicon? Share your thoughts in the comments and subscribe to discover more battery technologies.